So hello everyone, this is Easy Automation here, and today we are going to create some small projects in ladder logic. And while thinking of small projects, I thought why not create these logic gates first. So first we will create the basic 7 logic gates in the ladder diagram, and after that at the end of this video we will create one small project by which you will understand the basic concept of ladder logic. So before we start our session, you need to subscribe our channel if you are really interested in automation and turn on that bell icon as well. I need 100 subscribers before we hit monsoons. So let's begin. So let's start with our first logic gate, which is NOT gate. So for NOT gate, we need one NC contact and one output coil. So here you can see the ladder depiction of NOT gate, and the truth table of NOT gate is this. So let's check how NOT gate works. So the basic concept of NOT gate is the inversion concept, because if you are trying to toggle your input, the output will go off, and if you untoggle the bit, the output will go on. So here I will explain the NOT gate by one example. So just imagine you are trying to turn on a bulb by a toggle switch, and what would you do to turn on that bulb? You would just toggle that switch on and the bulb should go on. But in the case of NOT gate, it will happen inversely. Like if you are trying to turn on the bulb will go off, and if you are trying to turn off the bulb will go on. So this is the basic concept behind the NOT gate. Now let's move further to our next logic gate, that is AND gate, and I will just arrange the AND gate here. So for AND gate we need two NO contacts in series. Okay, so now that I have arranged two NO contacts in series and one output here, and this is the ladder depiction of AND gate, and this is the truth table of AND gate. So let's check how AND gate works. So if I toggle our first input, our output has no change, and if I untoggle this one and toggle our second bit, then also no change in output. But if I toggle our both inputs on, then our output is on. So this is the basic concept of AND gate. You can remember the AND gate by the example of your relationship. If both the people are interested in the relationship, then only the relationship will work. Otherwise, it doesn't work. Hashtag easy relationship advice. So this is the basic concept of AND gate. So let's move further to our next logic gate, that is OR gate. So I will just arrange the inputs according to OR gate. So for OR gate, we need to connect our inputs in parallel. So this is the ladder depiction of OR gate, and this is the truth table of OR gate. So let's check the truth table here. So if I toggle our first input, our output should go on, and if I untoggle this one, our output will go off. And if I toggle our second input, the output will also go on, and if I untoggle this one, then output will go off. And if I toggle both the inputs, then also our output is on, and if I untoggle both of these, then our output will go off. So this is how OR gate works. You can arrange as many inputs as you want in the parallel, so that you can turn on the output by any of the input which you are connecting in parallel. So this is the basic concept of OR gate. So let's move further to our next logic gate, that is NAND gate. And to create NAND gate in ladder logic, we need two NC contacts, and this is the ladder depiction of NAND gate, and this is the truth table of NAND gate. It is basically the inversion of AND gate. So let's check how it works. So if I toggle our first input, our output should not go off. Yes, it is still on. And if I untoggle this one and toggle our second input, then also our output is on. And if I toggle our both inputs, then only our output is on. So this is the basic idea behind the NAND gate. Our both inputs or the inputs in parallel and NC should off, so that our output should go off. And basically the NAND gate is used in two-step locking, where our output is going off only if both inputs are on, like this. So this is the basic concept of NAND gate. So let's move further to our next logic gate, that is NOR gate, and which is basically the inversion of OR gate. So let's just arrange. So this is how you can create NOR gate in ladder logic. You need two NC contacts in series and one output. So let's check the truth table. So the truth table of NOR gate says if I do not make changes in any inputs, then our output is on, and if I turn on any of the input, our output should go off. So if I toggle our first input, our output will go off, and if I untoggle this one, our output will go on again, and if I toggle our second input, then also our output is off, and if I untoggle this one, our output will turn on again. So this is the basic concept behind the NOR gate. So the truth table of NOR gate is basically the inversion of OR gate, as you can see here, and this NOR gate is used in interlocking. Imagine our first input is the emergency switch, and our second input input is stop button, and let's consider our output as motor. So if I toggle our emergency switch, our motor is off, and if I untoggle this one and toggle our stop button, then also our motor should go off. So this is how the NOR gate is used in industries. So let's move further to our next logic gate, which is little bit complex, but I will just explain it in easiest way possible. So let's just create the XOR gate in ladder diagram. So to create XOR gate in ladder diagram, we need one branch instruction here. So this is the ladder depiction of XOR gate. So there are two inputs which are used simultaneously, NC and NO as well. And you can see here I have used I colon 0.0 to our NC contact and NO contact as well, and I colon 0.1 to NC contact and NO contact as well. So this is how you can create XOR gate in ladder diagram. Now let's check the truth table of XOR gate, where if I toggle any of these two inputs, our output should go on, and if I untoggle both the inputs or toggle both the inputs, our output should go off. So first I will toggle our first input, then our output is on because the supply is going from this NO contact to this NC contact and to our output. And if I untoggle this one, our NO contact will become NO again, and the supply will break here and our output is off. And if I toggle our second input, then our output is on because the first input is NC here and the NO contact has become NC because I have toggled it. So that's why our output is on. And what if I toggle both the inputs? So toggle our first input, toggle our second input, then our output is off because the supply is coming from this side to this NO contact which has become the NC, but this NC contact has become NO because I have toggled the second input, and this NO contact has become NC, but there is no supply coming from this NC contact because I have toggled this first input. So this is the basic concept behind the XOR gate, where you need to turn on any one input so that our output should go on, and if you turn on both the inputs, our output will go off, and if you turn off both the inputs, then also our output will go off. The output will only turn on if you toggle only one input at a time. So this is how our XOR gate works. So now let's move further to our XNOR gate, which is just the inversion of XOR gate. So to create XNOR gate, we just need to put this NC contact with the another NC contact in series, and this NO contact with another NO contact in series. So this is the ladder depiction of XNOR gate, and this is the truth table of it. So now let's check how it works. So as I said, the truth table of XNOR gate is basically the inversion of XOR gate, as you can see here. So our XNOR gate says if I don't operate any of these inputs, our output is on. As you can see here, output is on, and if I toggle any of these inputs, one or two, our output will go off, and if I toggle both the inputs, then also our output will go on. So let's check. If I toggle our first input, then our output will go off, which was initially on, and if I untoggle this one, our output will go on again, and if I toggle our second input, our output will go off, which was initially on before toggling, and if I untoggle this one, our output is on. And what if I toggle both the inputs? Now let's check by toggling both the inputs. So here you can see our output is on because the supply is going from this NO contact which has become NC, and this NO contact which has also become NC because I have toggled them to our output. So this is how our supply goes to our output, and if I toggle both the inputs off, then our output is still on because the supply is going from these NC contacts to our output. So this is the basic concept behind the XNOR gate. So now that we have completed all the logic gates in ladder diagram, it's time to create one small project, and the problem statement for the small project goes like this. Imagine there are three processes in the factory and we need to create one alarm system for it, and the conditions are if any one process is harmed or stopped, the orange light should go on, and if any two processes are harmed or stopped, the red warning light should go on, and if all the processes are harmed or stopped, then both orange and red light should stop and alarm should start. So let's arrange the inputs and outputs as per the conditions. So for first condition, we need to add one rung here, and and add one contact, add one branch instruction, and add another contact, and extend branch down for third input. So I have arranged three contacts in parallel because there are three processes and one output coil. And for the output, I will name it as orange light. And for our input, name it as process 1, process underscore 2. And for our third input, I will name it as process underscore 3. So this rung is used for our first condition. Now let's create our second condition in another rung. So for second condition, we need one branch instruction here. So as the second condition says, if any two processes are harmed or stopped, the warning light should go on. So that's why I have took here two contacts in series and one output here. I will name this output as red light. So I have named this output as red light. And since these two conditions operating on same processes, I will just copy these for second condition. So for the first branch in the second condition, I am using process 1 and process 2 in series, and for second branch I will use first process and third process in series, and for the third branch I will use second process and third process in series, so that our red light should go on whenever any two conditions happen. So this is how we can create our second condition. So let's move further to our last condition. So for last condition we need another rung, and I will just use three contacts in series and one output coil, which will be named as alarm. So this is the last condition. I will just copy the inputs from second condition. So as our third condition says, if all the three processes are harmed or stopped, our alarm should go on. And there is another condition in third condition, that is when our alarm gets on, then our red light and orange light should stop. So for that I will just use here one NC contact in both the conditions, and I will just give the address from alarm to these NC contacts just like this. Now when the third condition occurs, like the alarm is on, then this NC contact will become NO and this will also become NO, by which our red light and orange light will stop. So let's verify this program. So verified, no errors found. So let's go online. So it is time to check whether our program is actually working or not. So as our first condition says, if any one input is on, then our orange light should go on. So our orange light is on here, and if I untoggle this one and toggle our second input, then also our orange light is on. And if I untoggle this one and toggle our third input, then also our orange light is on. So our first condition is satisfied here. Now let's move to our second condition. As our second condition says, if any two processes are harmed or stopped, then our red light should on. So I have toggled process 1 and process 2, then our red light is on. And if I untoggle process 1 and process 2 and toggled our process 1 on again and process 3, then also our red light is on, because the supply is coming from process 1 to process 3 and through this alarm to our red light. And if process 2 and process 3 are harmed, then our red light, then also our red light is on, because the supply is coming from the process 2, process 3, from alarm to the red light. So this is how our second condition works. So now it's time to check our third condition, which says if all the processes are harmed or stopped, then our alarm should go on. So let's toggle our first process. Our first process is stopped. Then I will toggle our second process. Then I will toggle our third process. And as you can see, our alarm is on and both orange and red lights are stopped. So now we will check all the conditions at the same time. So if our process 2 is harmed, then our orange light is on. And if our third process is harmed, then orange light and red light is on. And if our first process is also harmed, then alarm will go on and red light and orange light will go off. So this is how our program will work in real time. So I hope you have got something new today. Now it's your turn to create your own projects like these and try your own logic for it. And if you didn't understood any point in this video, feel free to ask in the comment section. I will always be there to answer your questions. And since we have created all the logic gates in the ladder diagram, you can try them on your own PC and laptop and compare them to get the actual idea how they work. And if you really enjoyed my teaching, then make sure to hit that like button. I am hoping for 100 likes. So help me reach that goal. With that being said, I'll be back in the next video. Bye. Subscribe.